In July 2024, on the floor of an ancient Martian riverbed, a robot drilled into stone. What it found shouldn't exist. Spots. Millimeter-sized spots surrounded by black rings, like the pelt of some cosmic leopard frozen in rock for 3.5 billion years. On Earth, these patterns form in only two ways: through the chemistry of life, or through chemistry that feeds life. But that's not the anomaly I want to tell you about. Because 120 light-years away, orbiting a red dwarf star in the constellation Leo, there's a world called K218b, 8 times more massive than Earth, wrapped in an atmosphere of hydrogen and water vapor. And in April 2025, the James Webb Space Telescope detected something in its atmosphere: a molecule, dimethyl sulfide. On Earth, every molecule of it, every single one, comes from life. 2 worlds, 2 potential biosignatures, discovered within 9 months of each other. The universe has posed humanity a question, not with words, but with chemistry, with spots on a rock, with molecules in alien air. Are we alone? Or are we about to discover that we never were? Let us begin, not with the familiar, but with the strange. 124 light-years from Earth. That's 730 trillion miles. If you could travel at the speed of the Voyager spacecraft, the fastest thing humanity has ever built, it would take you 2.2 million years to reach it. And yet, we can see it. Not with our eyes, of course. We see it the way astronomers see most worlds beyond our solar system, as a shadow, as a dimming. Every 33 days, K218b passes between us and its star, blocking a fraction of the star's light. But here's what transforms a mere shadow into a revelation. Some of that starlight, just a fraction of it, passes through the planet's atmosphere on its way to us. And as it does, molecules in that atmosphere absorb specific colors, specific wavelengths. They leave fingerprints. Think of it as a kind of chemical archaeology. We're reading the composition of alien air by studying the colors it steals from starlight. And in September 2023, when the James Webb Space Telescope turned its infrared eyes toward K218b, it found something remarkable in those fingerprints: methane, carbon dioxide, and water vapor. Not just traces, abundant water vapor. Perhaps, and this is where the story becomes tantalizing, perhaps enough to suggest a world-spanning ocean beneath that hydrogen-rich atmosphere. A Hycean world, they call it, from hydrogen and ocean. A planet utterly unlike Earth, and yet potentially habitable. A place where, billions of years ago, life might have found a way to begin. But water and methane aren't biosignatures, not on their own. They tell us about possibility, not proof. So the astronomers looked again, deeper, looking for something that life, and only life, might make. They found dimethyl sulfide, 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom binding it all together. The molecular formula, C2H6S. On Earth, this molecule has a particular smell. You know it, even if you don't recognize the name. It's the smell of low tide, of seaweed decaying on beaches, of the ocean itself. Because on Earth, dimethyl sulfide comes from phytoplankton, microscopic algae in the sea. They produce it as a byproduct of their metabolism. billions upon billions of tons of it every year. It rises from the oceans, drifts through our atmosphere, and becomes the seeds around which water droplets form, eventually falling as rain. Life making weather, weather sustaining life. And no abiotic process, no non-living chemistry, has ever been observed producing it in significant quantities on Earth. So when Niku Madhusudan and his team at Cambridge reported that tentative detection in September 2023, and then claimed stronger evidence in April 2025, reaching what they called 3 sigma confidence, the implications were staggering. But here's where our story enters its messy middle. Because science isn't a straight line from question to answer. It's a conversation, a debate, a process of claim and counterclaim, of certainty questioned and evidence examined from every angle. By July 2025, other teams had reanalyzed the same data, using different techniques, different assumptions, different data reduction pipelines. And they found something else. Luis Wellbanks at Arizona State identified 59 different compounds that could produce similar signals in the data. Propyne, a simple hydrocarbon, might fit even better than dimethyl sulfide. When you detect everything, Wellbanks said, did you really detect anything? By August, a NASA-led study titled K218b does not meet the standards of evidence for life, found that when they analyzed the data their way, 87.5% of their models didn't support the presence of dimethyl sulfide at all. Kevin Stevenson, lead author, put it bluntly. We found that the Miri transit spectrum is highly susceptible to unresolved instrumental systematics. Translation: noise, uncertainty. The inherent difficulty of measuring something so faint, so far away. So where does that leave us? With a world we can barely see, whose atmosphere we're trying to read through 730 trillion miles of space. With a signal that might be life's first whisper across the cosmic ocean. Or might be nothing more than starlight and statistics playing tricks on our instruments. With the uncomfortable realization that maybe is often the most honest answer science can give. And yet there's another world. Closer, much closer, where another kind of maybe awaits. Jezero Crater, 28 miles across, located just north of the Martian equator. 3.5 billion years ago, this wasn't a crater. It was a lake. Picture it. Water flowing down from the highlands, carrying mud and silt and gravel, rushing through river channels, one of them 400 meters wide, and emptying into this ancient basin. A lake that might have persisted for millions of years, deep enough, calm enough, stable enough, for something to begin. And then, over geological time, Mars dried. The atmosphere thinned. The water disappeared, locked into polar ice, absorbed into the soil, or lost to space. The lake became a crater. The rivers became valleys of dust and stone. But the rocks remember. On February 18, 2021, a spacecraft named Perseverance landed on the floor of Jezero Crater. The 5th successful Mars rover, the most sophisticated scientific laboratory we've ever placed on another planet. Its mission? To search for signs of ancient microbial life. Not to find life itself. Mars is almost certainly lifeless today, its surface scoured by radiation and cold. But to find what life might have left behind. Fossils, organic molecules, chemical signatures that whisper, something was here, something lived. For 3 years, Perseverance has roved across Jezero. drilling cores, analyzing rocks, collecting samples that one day a future mission might return to Earth. And on July 18, 2024, on the rover's 1212th Martian day, it found something. An arrowhead-shaped rock, 3.2 feet by 2 feet, partially buried in what had once been a riverbed. The science team nicknamed it Cheyava Falls, after a waterfall in the Grand Canyon. A name chosen because, like that waterfall, this rock had stories of ancient water written into its very structure. Look at it closely. Running through it, like veins of pale lightning, are streaks of calcium sulfate. That's gypsum, a mineral that forms when water carrying dissolved calcium and sulfate evaporates or cools. Evidence of water, ancient water, flowing through cracks in the rock. Between those white veins, bands of reddish material, hematite, iron oxide, rust, the same mineral that gives Mars its distinctive color. But it's what sits within those red bands that captivated the scientists. Spots, millimeter-sized, irregularly shaped, off-white cores surrounded by thin, dark rings. They called them leopard spots. Now, here's where we need to slow down, because what happens next is not simple. And the temptation, the overwhelming temptation in science communication, is to rush to the conclusion. To say, leopard spots mean life, and move on. But that would be doing a disservice to the complexity, to the beauty of the scientific process, to the very thing that makes this discovery so compelling. So let's understand what these spots actually are. The dark rings contain two iron-rich minerals, vivianite and gregite. Vivianite is hydrated iron phosphate, a mineral that forms when iron in rocks receives electrons, when it's chemically reduced, in the presence of phosphorus and water. Gregite is iron sulfide, another product of chemical reduction. On Earth, we find minerals like these in very specific environments, places where organic matter is decaying, where microbes are breaking down dead organisms, stripping electrons from those organic molecules and handing them to iron in the surrounding rock. The iron changes, from rust-red ferric iron to pale ferrous iron. And as it does, it forms these distinctive patterns, these spots, these halos. We see it in Earth's ancient rocks, in lake beds that dried millions of years ago, in sediments where once, long ago, microbial life thrived. And here's the extraordinary thing. When researchers try to reproduce these patterns in the laboratory under controlled conditions, they get vivianite and gregite in the samples with live microbes, but not in the sterile controls. So the pattern suggests biology. The minerals suggest biology. The association between organic molecules and these spots, Perseverance detected organic compounds in the same areas, suggests biology. But there are other possibilities. Chemistry without life, abiotic processes. Perhaps the rock experienced high temperatures, hot enough for chemical reactions to produce similar patterns without biology. But there's no evidence the rock was ever that hot. Perhaps acidic water catalyzed these reactions, but there's no evidence of acidic conditions. Perhaps some process we don't fully understand, some Martian chemistry we've never witnessed on Earth. Amy Williams, a member of the Perseverance team, said it best. The discovery of life beyond Earth is so profound, so paradigm-shifting, you have to get it right. Once you cross that line, you can't come back. After a year of study, a year of analyzing, debating, peer-reviewing, The team published their findings in the journal Nature in September 2025. Their conclusion: no particularly strong evidence for any non-biological explanation. Not proof of life, but the closest thing to proof we've yet found on Mars. A rock that contains, in one place, all three requirements life needs: evidence of water, organic molecules, and a potential energy source. Acting NASA Administrator Sean Duffy called it the closest we have ever come to discovering life on Mars. But here's the thing about closeness, about almost, and nearest yet, and no strong evidence against. They're not the same as yes, and they're certainly not the same as proof. The sample sits now in a titanium tube, sealed, labeled Sapphire Canyon, stored aboard Perseverance millions of miles away. And there it will remain, because the rover has done all it can. It has asked all the questions its instruments can ask, performed all the tests its laboratory can perform. To answer the final question, to know, truly know, whether those spots were made by ancient Martian life, the rock must come home. The Mars Sample Return Mission, years in planning, designed to retrieve these precious cores and bring them back to Earth, where laboratories 1,000 times more sophisticated than anything on Perseverance could analyze them atom by atom, molecule by molecule. But in 2025, that mission was deemed financially unsustainable, proposed for cancellation by the Trump administration, and as of this recording, its future remains uncertain. The Economist compared it to the 2015 film The Martian, where astronaut Mark Watney is stranded on Mars waiting for rescue. Except in this case, what's stranded isn't a person, it's a rock. A rock that might rewrite our understanding of our place in the cosmos. A rock that's waiting, that might wait for decades, perhaps longer. And so we're left, once again, with maybe. Maybe those spots were made by life. Maybe we've found proof of ancient Martian biology, and it's sitting in a tube on a rover 140 million miles away, waiting for a rescue mission that may never come. Maybe. Let's pause here. In this uncomfortable space, this messy middle where most science actually lives. Because if you've been paying attention, you've noticed something that might make you uneasy. We have two discoveries, two potential biosignatures, and neither of them is certain. K218b, a molecule in the atmosphere that might be dimethyl sulfide, but might be propyne or ethane, or some combination of compounds we can't quite resolve. At 3 sigma confidence, meaning there's still a 0.3% chance it's just noise, just statistics, just instrumental artifacts. Mars. Leopard spots in a rock that look like biology, smell like biology, have minerals and organics consistent with biology, but for which we cannot rule out abiotic explanations. This isn't the story most people want to hear about the search for alien life. We want the moment of discovery, the unambiguous signal, the clear answer to the clearest question humanity has ever asked. We want the obelisk on the moon, the radio signal from Vega, the alien ambassador landing on the White House lawn. We want certainty. But the universe doesn't care what we want. Science is not a collection of facts. It's a process, a method for turning uncertainty into progressively less uncertainty. Not by leaping to conclusions, but by testing every hypothesis, questioning every assumption, demanding extraordinary evidence for extraordinary claims. Let me tell you about another time we thought we'd found life on Mars. August 7th, 1996. President Bill Clinton stood in the White House Rose Garden and announced that scientists had found potential evidence of ancient life on Mars, not from a rover, but from a meteorite. ALH 84001, a rock blasted off the Martian surface by an impact 17 million years ago, which eventually fell to Earth in Antarctica 13,000 years ago. Inside it, structures that looked like fossilized bacteria, magnetite crystals of the type produced by bacteria on Earth, organic molecules. Today, Clinton said, Rock 84001 speaks to us across all those billions of years and millions of miles. The media exploded. Life on Mars! The fossil evidence seemed compelling, the implications staggering. But then came the scrutiny. Other scientists examined the same rock, performed different tests, proposed different explanations. The fossils might be mineral structures formed by non-biological processes. The magnetite crystals could have formed through heating, not biology. The organic molecules might have contaminated the rock after it landed on Earth. Within a few years, the consensus had shifted, not to definitely not life, but to probably not life, almost certainly not life. The evidence doesn't hold up. That's not a failure of science. That's science working exactly as it should. A bold claim met with skepticism, tested rigorously, and when the tests didn't support the claim was revised. We moved on, wiser, more careful, better equipped to recognize what evidence for life actually looks like. Or consider Venus. In September 2020, astronomers announced the detection of phosphine in Venus's atmosphere, a gas that, on Earth, is produced primarily by life or industrial processes. The media went wild. Life in the clouds of Venus! But then, controversy. Other teams reanalyzed the data and found the signal wasn't as strong as initially claimed. Some found no phosphine at all. Others suggested alternative explanations, volcanic activity or photochemistry in the upper atmosphere. As of today, the phosphine claim remains controversial, uncertain, debated. This is how the search for life proceeds, not with eureka moments, but with incremental steps, claims and counterclaims, data and debate. So why am I telling you this? Why dwell in the uncertainties, the controversies, the failures? Because this is what makes the current moment so extraordinary. For the first time in human history, we have the technology to actually search for biosignatures on other worlds, not through speculation or philosophy, but through chemistry, through spectroscopy, through direct physical investigation. The James Webb Space Telescope can analyze the atmospheres of distant planets, looking for the chemical fingerprints of life. Perseverance can drill into Martian rocks and perform sophisticated chemical analyses on another planet's surface. We're living in the age, the very first age, when humanity can ask, "Are we alone?" and begin to receive actual data in response. That data will be messy. It will be uncertain. It will be controversial. Because we're at the very beginning of this search. We're learning what biosignatures look like in contexts utterly unlike Earth. We're developing new instruments, new techniques, new ways of interpreting what we find. Niku Madhusudan, whose team reported the K2-18b results, said this: "We have entered a new era in the search for life beyond Earth, where it is possible to detect and debate about potential biosignatures. This is unprecedented. Detect and debate. That's the key phrase. We're not claiming to have found life. We're claiming to have found things that might be signs of life. And that, the very possibility of making that claim, of having data good enough to debate about, is revolutionary. Because here's what these two discoveries represent, taken together. Not proof, but the vanguard. The first tentative, uncertain, controversial steps toward answering the oldest question. Let's zoom out. Not just from Mars and K2-18b, but from this moment in history. From this particular instant in the 13.8 billion year story of the universe. And let's ask, what are we actually looking for? The obvious answer is life. Other life. Proof that biology is not unique to Earth. That we are not, as far as the universe is concerned, alone. But I think it's deeper than that. We're looking for context. Think about what it means to be human, to be conscious, to wake up in a universe that seems, on first inspection, to be made of stars and space and silence. We evolved on a planet teeming with life. Every breath we take is oxygen produced by photosynthetic organisms. Every bite of food we eat was once alive or was made by something alive. The very cells in our bodies are descended from ancient bacteria that merged in symbiosis billions of years ago. Life, for us, is not exceptional. It's the baseline. It's everywhere. But when we look beyond Earth, what do we see? Rock, ice, gas, radiation. Beautiful, yes. Wondrous, yes. But seemingly empty. And so we're forced to confront a possibility that's both humbling and terrifying. Maybe we're it. Maybe, in all the vastness of space, on all the worlds circling all the billions of stars in all the galaxies, we're the only ones looking back. The only ones asking questions. The only ones trying to understand. That would make us not just rare, but cosmically precious. The universe's way of knowing itself. Consciousness, somehow, impossibly, emerging from matter and looking back at the void from which it came. As Carl Sagan said, we are a way for the cosmos to know itself. But there's another possibility. Maybe life isn't rare at all. Maybe, given the right ingredients, liquid water, organic molecules, an energy source, life emerges as naturally as crystals forming in a cooling liquid. Maybe the universe is full of life. Microbes in subsurface oceans, bacteria metabolizing sulfur in the clouds of gas giants, ecosystems we can't even imagine, thriving in environments we'd consider hostile. If that's true, then we're not precious. We're typical, part of a cosmic pattern. Life as a fundamental feature of the universe, like gravity or electromagnetism. And finding even one example of life beyond Earth, even a single microbe on Mars, even a whiff of biosignature gas on K2-18b, would suggest that life is common, that we are, in the most profound sense, not alone. So which is it? Are we the exception or the rule? This is what leopard spots on Mars and dimethyl sulfide on K218b are really about. They're not just scientific curiosities, they're attempts to answer the most fundamental question about our place in existence. And here's what's both beautiful and maddening about our current moment. We might be on the verge of answering that question. Not definitively, perhaps. Not with absolute certainty, but with enough confidence to shift our understanding of what life is, where it can be, what it means to be alive in this universe. The generation growing up right now might be the first to know. To live in a universe where "Are we alone?" has been answered. Not with philosophical speculation, but with chemistry, with evidence, with data. But we're not there yet. We're in the waiting room, the anticipatory moment, the place between question and answer where anything seems possible. And in a strange way, this might be the most exciting time of all. Because once we know, once we definitively know, that moment of discovery becomes history. The question becomes a fact. The mystery resolves. But right now, right here, in this particular moment of human history, we don't know. And that not knowing is itself a kind of treasure. Consider what we've learned in just the last few years. JWST has shown us that planets around other stars have rich, complex atmospheres, that we can measure their composition from trillions of miles away. Perseverance has shown us that Mars, 3.5 billion years ago, was a world of rivers and lakes, a place where, if life emerged, it would have found conditions suitable for survival. We've discovered that organic molecules, the building blocks of life, are everywhere in space, in comets, in the interstellar medium, raining down on every rocky world. We've found that even on Earth, life thrives in the most unexpected places, in boiling hot springs, in Antarctic ice, in rocks miles underground, in the crushing pressures of the deep ocean. Life, we've learned, is not fragile. It's tenacious, adaptable, relentless. So why not Mars? Why not K218b? Why not somewhere? Of course, there's still the question of what we mean by life. Is it metabolism, growth, reproduction, evolution? All of the above? Are viruses alive? They reproduce, they evolve, but they can't metabolize on their own. What about self-replicating molecules? RNA that can copy itself? What about artificial intelligence? If it ever becomes truly self-aware, would we count that as life? These aren't just philosophical questions, they're practical ones. Because if we find something on Mars, or K218b, that doesn't quite fit our definitions, chemistry that's self-organizing but not quite alive, not quite not alive, how do we classify it? How do we answer, "Are we alone?" when we're not even sure what "we" means? Here's what I think. I think the search for life elsewhere is ultimately a search for understanding ourselves. We look out at the universe and see our own reflection, our own story, the story of how matter became complex enough to contemplate its own existence. And we wonder, did this happen before? Elsewhere? Are there others out there, on distant worlds, looking up at their own skies and asking the same questions? The answer, whatever it turns out to be, will change us. If we find life, even microbial life, we learn that biology is not a fluke, that given time and chemistry, life finds a way. And we'll know that, somewhere in this vast universe, there are probably other worlds where life has done more than just survive, where it has flourished, where it has, perhaps, become conscious. If we don't find life, if we search and find nothing but empty worlds, we learn that we are staggeringly lucky, that existence, consciousness, intelligence are so rare that we might be the only examples in billions of light years. And that would make every human life, every human achievement, every act of kindness and creativity and courage infinitely precious. Either answer transforms us. Let's return now to our two worlds. Mars, a world that once was. Ancient rivers, ancient lakes, ancient possibility. Now frozen, desiccated, seemingly dead. But perhaps, just perhaps, once alive. K2-18b, a world utterly unlike anything in our solar system, neither rocky like Earth nor gaseous like Jupiter. A sub-Neptune, a water world with a hydrogen atmosphere. If life exists there, it would be life as we've never imagined it. Biology adapted to conditions alien beyond our experience. Two worlds, two different kinds of evidence, two different challenges for interpretation, but one question. Let me tell you what makes this moment in history so extraordinary, beyond the discoveries themselves. It's that we're searching simultaneously on multiple fronts. NASA's Europa Clipper, launched in October 2024, is on its way to Jupiter's moon Europa, a world with a subsurface ocean that might harbor more water than all of Earth's oceans combined. The Dragonfly mission will reach Saturn's moon Titan in 2034, a world with lakes and rain and complex organic chemistry, albeit with methane instead of water. JWST is observing dozens of potentially habitable exoplanets, building up libraries of atmospheric spectra, searching for combinations of gases that might indicate life. Future missions, like the Habitable Worlds Observatory, planned for the 2040s, will be designed specifically to search for biosignatures in the atmospheres of Earth-like planets around Sun-like stars. This is humanity, finally, mustering the resources and technology to systematically search for life beyond Earth. Not waiting for aliens to visit us, not listening passively for radio signals, but actively investigating, world by world, molecule by molecule. And Mars and K2-18b are the first two places where we've found something compelling enough to debate about. That's historic. Think about the process that's unfolding. The way these discoveries are being made and challenged and refined. Multiple teams, using different instruments, different techniques, different assumptions, all analyzing the same data. Some teams find signals, others find noise. Some argue for life, others argue for chemistry. This isn't a weakness of the scientific method. It's the method itself. This is how we separate signal from noise, reality from artifact, discovery from wishful thinking. And the beautiful thing, the thing that gives me hope, is that eventually the truth wins. Not because scientists are perfectly objective, not because every individual researcher rises above bias and preconception, but because the process, collectively, over time, converges on reality. Bad ideas get filtered out. Good ideas get strengthened. Evidence accumulates. Understanding deepens. So what happens next? For K2-18b, more observations. JWST will observe it again, building up signal to noise, confirming or refuting the dimethyl sulfide claim. By the late 2020s, we should know with much greater confidence whether that molecule is really there. And if it is? If we reach 5 sigma confidence, the gold standard for scientific discovery, then the next question becomes, is it biology or is it photochemistry? Is it life or is it just complex chemistry that mimics life? Answering that will require understanding the planet itself better, its temperature, its pressure, its radiation environment, whether it truly has an ocean or whether it's some kind of hybrid world we've never encountered. For Mars, the sample return, getting those tubes back to Earth, analyzing Cheyava Falls with instruments that can measure isotope ratios, detect molecular chirality, examine biosignatures that the rover simply can't access. But that mission, as I mentioned, faces enormous challenges. Budget constraints, political will, technical complexity. If it happens at all, it won't be until the 2030s at the earliest. Which means we wait. We wait for more data, more observations, better instruments, clearer answers. We wait in this liminal space between ignorance and knowledge, between loneliness and company, between Earth as the only known cradle of life and Earth as one example among billions. And while we wait, these two worlds, Mars and K2-18b, remind us of something crucial. The universe is not obligated to make it easy for us. If life exists on Mars, it's been dead for billions of years. Its remains are faint, ambiguous, barely distinguishable from geology. If life exists on K2-18b, it's 124 light-years away. We can't go there. We can't sample it directly. We can only look and infer and debate what we see in the starlight. This is the challenge we've inherited, not because we chose it, but because of when and where we happen to exist. In a time when we're just barely advanced enough to ask these questions, but not quite advanced enough to answer them definitively. Yet. Let me tell you what I think these two discoveries mean. Not what they prove, not what they definitively establish about life beyond Earth, but what they mean. They mean that the search for life is no longer science fiction. It's science fact. We are, right now, in this decade, finding potential biosignatures on other worlds, debating their meaning, planning follow-up observations, building better instruments to answer these questions. They mean that maybe is the most exciting word in science, because maybe contains all possibilities. Maybe means the question is still open. Maybe means there's still mystery in the universe, still room for wonder, still frontiers for exploration. They mean that uncertainty is not a weakness. It's honest. It's humble. It's the acknowledgement that reality is complex, that evidence is difficult to gather, that extraordinary claims require extraordinary scrutiny. And perhaps most importantly, they mean that we're asking the right questions in the right way. This is a global effort. Astronomers and astrobiologists from dozens of countries, sharing data, challenging each other's interpretations, working together to understand what we're seeing. This is humanity at its best. Curious, rigorous, open to wonder, demanding of evidence. Let me leave you with a thought. Those spots on Cheyava Falls, whether they were made by life or not, they were made by chemistry, by atoms and molecules interacting according to the laws of physics billions of years ago on a world that was once wet and possibly habitable. That potential dimethyl sulfide on K2-18b, whether it's a biosignature or not, it tells us that planet has a complex atmosphere, that molecules form and break apart in alien skies, creating chemistry we're only beginning to understand. And isn't that in itself extraordinary? We live in a universe where planets form around stars, where chemistry becomes complex, where, at least once on Earth, complex chemistry became biology, and biology became consciousness, and consciousness began asking questions about its own origins. Whether that's happened elsewhere or not, the fact that it happened at all is miraculous. We are, every one of us, made of stardust. Atoms forged in the hearts of dying stars, scattered across space, eventually coalescing into rocky worlds, and on at least one of those worlds, arranging themselves into patterns complex enough to contemplate their own existence. Look again at those two worlds. Mars, so close we've landed robots on its surface. K2-18b, so far that light from its star takes 124 years to reach us. Two worlds among trillions. Two potential signals in an ocean of silence. Maybe they'll pan out. Maybe they won't. But the search continues, because we are a curious species, because we want to know. Because the question, are we alone, demands an answer, even if that answer takes decades or centuries to find. And someday, maybe in our lifetimes, maybe in our children's lifetimes, we will know. We'll find unambiguous evidence of life beyond Earth, or we'll search thoroughly enough, long enough, carefully enough, to conclude that if life exists elsewhere, it's extraordinarily rare. Either way, we'll know. Until then, we have these maybes, these possibilities, these leopard spots, and these molecules in alien air. We have the privilege of living in the age when humanity first began to seriously search for life beyond our world. We have the honor of uncertainty, of not knowing, of standing at the threshold of one of the greatest discoveries our species could ever make. Two worlds, one question, and all of human history waiting for the answer. The search continues. This is Cosmic Canvas, where we trace life beyond Earth. Until next time, remember that the search for life isn't about the destination. It's about becoming the kind of species worthy of finding it.